we are finally ready for the seminar with LeClair from Cornell, which will talk about some new perspective about Riemann hypothesis. Right, please.
Thank you very much. Thank the organizers for the opportunity to do this talk here, especially since they don't quite fit in. I know there won't be too much entanglement, lunches. Actually, won't be any physics either. So, but at least 3 of the 4 organizers have some interest in this problem. In fact, I learned about the problem from that month when we were working together on certain cyclic RG flows, and the zeta function in the complex plane was showing up, not in the right region. So, you know, I know I tried hard to find some model that got us into the critical strip. In fact, I'll make if you don't understand this terminology, I'll be reviewing it in a moment. But anyway, I gave up on the physics approach. Riemann wrote a series of papers continuing.
You gave up on physics?
Well, almost. At least for the last 3 years. So, Giuseppe's had a long-term interest in this. Had long conversations with him. He has some long lecture notes on number theory. I've had long discussions with Denis. Fabian, I'm not sure he really believes in the Riemann hypothesis. I have no idea. In any case, so let me start here. So in any case, I think everybody knows it's an important unsolved problem, 150 years old. It's mainly be a blackboard topic, right? That word disappears. So why is this important? Well, for one thing, it's almost an embarrassment to mathematics that hasn't been solved yet. But the importance is that it has to do with the prime numbers. So the Riemann hypothesis is, I will give the background in a moment, but it's a question about where the zeros of this function lie. Okay? But the importance is that those zeros know about where all the prime numbers are. So you define this prime number counting function, sum over all primes, less than a certain value, 1. So it's just the number of primes less than x. Well, there's a leading term. Well, this is the x, that notation. This approximately goes as x over log x. And then there's some corrections. This is a very smooth function, but of course this is a staircase function. It has to jump by 1 to be 0. So there's all these corrections that turn it into precisely a staircase function. These are fluctuations, if you like, but they're characterized by all the non-trivial Riemann zeros. It's an infinite sum over the non-trivial zeros, and it's known as an infinite number of them. And it's fun to play with this numerically. You can say include, say 50 zeros, and start seeing this turn into a nice staircase function. So plot pi of x. This, the smooth part, just gives you a smooth curve. But then when you start adding these fluctuations, then you start, you know, at 2 you jump by 1, at 3 you jump by 1, and at 5 you jump by 1, etc. So the first prime here is 2. 1 is not a prime. Emphasized to me. So there's so the references are, there's a couple of papers. One from, so this has been work going on about 2 to 3 years. This one's an actual journal. Come on, Fizz. The other one is with Franz, my postdoc. Here, this one we're happy with because it appeared in the Communications Number Theory in Physics, which has physics in the title, but it is a pure math journal. And there's a couple others that are in the works.
Sorry, what is the CMTP?
Communications and Number Theory in Physics.
I see.
So there's
a question on this.
There's a couple papers that are in the, yeah.
Quick question, sir. Since it's like new subject of this one, can you comment what is exactly 150 years old? What is
Yeah, well, I mean, I'm gonna
like
do
this
that.
is old result or this is?
I'm gonna explain, I'm gonna give all the background in a moment here. So I'm just trying to get to, you know, for people who know a bit about the problem, just try to give some of the main points. sorry, so completely describe the full background of the problem, but, oops, how's this gonna work? You saw it. But the main point, like, you can carry away in this talk is the following few points. So the sort of main results or just phone points.
Can you avoid writing in the shadow because we don't see?
Yeah,
Just write under and probably.
maybe just,
Yes, this is better.
so, so the Riemann hypothesis is kind of peculiar in that there's no well-defined strategy to prove it yet in the math literature, as far as I can tell. This is different than, say, Fermat's last theorem, where it was already known that if you proved certain equivalence between some elliptic curves and some modular forms, in fact, I'll be talking about modular forms, then if you prove that, that was equivalent to proving the Fermat's last theorem. So that's what Wiles did. So there was already a well-defined strategy toward proving it. For Riemann, I don't know of any such strategy, but I certainly will be presenting one here and proving at least a few theorems. So, where, if there's no clear strategy, why is it true? It's apparently true. People have checked that it's true to very high heights. But why? And I'm going to claim that Riemann hypothesis follows from some properties of the primes. A kind of randomness of the primes, which is what I call pseudo-random. That's a very clear statement. This is going to have to be careful. I mean, the primes are not completely random. They're ordered. You know, there's probably an infinite number of twin primes. So this is going to have to be characterized. And it's going to be in terms of some random walks. So what we see is that certain series built over sums over primes, because the primes are essentially their pseudo-randomness is really just because they're multiplicatively independent. It's going to least some random walk properties. And from that, the Riemann hypothesis would follow. The second point,
If they
which
were
is
completely random, the twin primes would also follow.
if they were completely random, it may be, yeah. Yeah.
And what is the observation?
I think there are proofs that if you have a.
I didn't get what the comment was.
Well, yeah.
Go ahead.
I was just point, twin prime conjecture was mentioned, but if primes were in fact randomly chosen, I mean, if you just choose a random infinite selection of numbers, then you would.
Yeah, there's some random models of the primes, like Cramer's model. So you assume some probabilistic model where the primes are, and if you assume that, then you can prove certain things.
I know it.
Like, okay.
No, indeed, if it's purely random, Riemann hypothesis straight away from the very beginning.
I think so, yeah.
Yeah, it was
If
random.
the primes are,
It's
yeah,
it's
completely
proved
random.
straight away.
So here, this is different from what's going the opposite direction. Also, so the zeros, there is an infinite number of zeros in the so-called critical strip, and we have some exact equations that are mu for individual zeros. Which we can solve numerically, we get very good results. And actually, this is going to involve the product formula. So these two things combined lead to some kind of new algorithm. For this is kind of awkward for computing zeros. And as I set myself a goal, I mean, some very high zeros are known, up to the 10 to the 33rd, or the 22nd. So I set myself the goal of calculating the Google zero, the 10 to the 100th zero, and I can present so. So now in answer to the first question I got, now, if you've never heard about this problem, let me explain the various terminology of what the problem actually is. Okay, so this is just background. And this will take maybe 15 to 20 minutes, and then I'll get start doing what we actually do. So the zeta function, so in so-called analytic number theory, the complex plane, the complex variable, is traditionally written as sigma plus IT. So we're working in a complex S plane. And originally the series was defined as sum over all integers. Yes. And well, this series converges for the real part of S greater than 1. And well, what Riemann did was show how to analytically continue it into the whole complex plane. Now, there's two very fundamental properties of this function, which many people believe are there's lots of other functions that are thought to satisfy Riemann hypothesis, and they're all partly based on counterexamples. They're all believed to have two important properties. One is the functional equation, and the other is the Euler product formula. So let me tell you about the functional equation. This was known to Riemann. So if you define a so-called completed zeta function, multiply it by pi to the minus s over 2, standard gamma function, zeta of s, then this function satisfies a very nice functional equation. Chi of s is really chi 1 minus s. So already you see the importance of the critical line. You can do it because clearly on the read line, what half is important here. So, I mean, there's many proofs of this, and it was in Riemann's original paper, which, by the way, was only like a 5 or 6 page paper. But for the people in this audience, people studying conformal field theory, I think they're well aware of one example, so just mention it, so this is not such a mysterious equation. So a little bit of CFT, 2D, remind you where this has come from. Let me take a free boson on the cylinder. Okay, so geometry looks like this. And so this has the state data, the circumference. So you can view this two different ways. You can view this, take this to be space, and take the circumference to be Euclidean time. Then you've compactified Euclidean time, so you're talking about finite temperature field theory. Okay, so beta is related to an inverse temperature. Then you can calculate the free energy. Everything is convergent. It's a certain integral over the Bose-Einstein distribution. And if you calculate it, it's going to involve, it's proportional to zeta of 2, which you may remember is pi squared over 6. Indicates the answer you get is minus pi over 6 t squared. Okay, so this is the analog of the Stefan Boltzmann law in one spatial dimension. Okay. Everything's convergent, no problem. On the other hand, if since this is Euclidean space, I could just as well view this as time, and this is space. It's a kind of modular transformation. So now physics is very different. You're at 0 temperature. There's no temperature here anymore. What you're actually calculating is a ground state energy. It's basically the modes, momenta are quantized along the circle, and then the ground state energy is an infinite sum. So in this picture, what you're calculating is 0-point energy, ground state energy. And the interesting thing about it is that is how it depends on beta. Okay? Now, in doing this sum, basically you just have an infinite number of quantized oscillators. You're going to encounter zeta minus 1. Okay. So zeta minus 1 in the sum, well, of course, is 1 plus 2, formally plus 3 plus 4, which is obviously divergent. But Riemann told us how to analytically continue the zeta function. And after, this by itself makes no sense, but after analytical continuation, you get this minus 112. And then using this in factors of pi, etc., you get the same answer. So I always found it kind of remarkable because somehow nature knows. I mean, you can measure this 0-point energy. In fact, this is a bit like calculating the cosmological constant. Nature somehow knows about analytic continuation. So here we go again. Maybe I'll just keep erasing. Yeah. Let me stick with this one. So we're going to use that. Oh, one other application of, well, something else is going to play a role that does have an other physical interpretation, that zeta has a pole at s equals 1. Physically, this is explains why there's no Bose-Einstein condensation in two spatial dimensions. If you look at the critical density, try to calculate it, you're going to encounter zeta 1. And it blows up, which is why there's no BC. In D equals 2 spatial dimensions. That's the end of the physics, by the way. All right. So we're interested in the zeros. You're trying to solve, so zeros are known as rho. You're trying to solve this equation. It's one equation. Well, it's two real and imaginary parts. It has an infinite number of solutions. Later on in the talk, I'm going to replace this single equation with an infinite number of equations, one for each individual zero. We'll get to that later. But anyway, where are the zeros? So this is where the standard terminology comes from. Here's the pole at 1. There. So the critical line is halfway between. Half. Now there's some trivial zeros out here. So I'm denoting zeros by x's. So at -2, -4, every negative even integer, there's a 0. Those are so-called trivial. You can understand them from the functional equation. If you look at the functional equation, remember it involves a gamma function. So where the gamma function has a pole, which it does at negative integers, then that will give you a 0 zeta. Okay, so the non-trivial ones are the ones here. And it's already known there's an infinite number of them along this line. Without reflection symmetry, the same as down here. So the Riemann hypothesis is whether this exists. Okay. So the Riemann hypothesis is that all zeros are on some critical line, which is real part of S. So simply stated.
Sorry.
Yeah.
The zeros that have been found numerically,
Mhm.
do we know exactly that they are on this line, or just we have
So-
a very good approximation?
Yeah, so the reason people have strong numerical evidence that it's true is that numerically, people have checked that up to the 10 to the 13th zero are all on the critical line.
But exactly on the critical line.
Exactly in the critical line. So there's a lot of numerical evidence. Now this brings me to the next main ingredient. Notice there's no zeros out here. Why? It's a simple way to understand that. RFS, question mark. And the answer is the other important ingredient, which is the Euler product formula, which is known to Euler.
You already said it that there is no zero. You said that C
What?
is convergent.
What?
You said that the series is convergent. Oh, yeah.
Just because it converges doesn't mean it's not zero.
I know zero. I was thinking about
It converges. So what? It might be zero.
It makes point.
Alright, so we're going to need this. So at least for, well, let me just write down the formula. So just fundamental arithmetic. Remember, this is a sum over integers of 1 over n. Yes, you can uniquely factorize any integer over primes. And then Euler realized that you can write this as a product then over primes. 1 over Pn s inverse, where Pn is the nth prime. So 2, 5, 3 primes. So now it's kind of clear because this is valid. This converges absolutely for real part of s greater than 1. So it's valid for to the right of this line. And obviously it's not zero. This right-hand side is never zero. If you want, you can phrase it in terms of log. If there was a zero, then the log of zeta would have to blow up somewhere. And it just doesn't because of this product formula. Now there's a famous theorem that tells you that in complex analysis, domains of convergence are always half planes. Okay, so you know, for instance, if S is real here, I know this converges along this line. In fact, if it converges anywhere at a certain point, it's going to converge everywhere to the right of that in the complex blend. Okay, so that's why just the fact that you get to check the convergence right here near the pole, then it's going to converge everywhere else. So we're going to use that later too. So mathematicians talk about abscissas of convergence. The abscissa is the real part, you know, and to the right things converge. And there's abscissas of absolute convergence and abscissas of convergence. Now, absolute convergence is a simple thing to check. Convergence itself is sometimes, sometimes kind of subtle. For reasons I'll explain. Let's try this. Are you still here? Yeah. Okay. So, well, one thing is going to be actually the main way I'm going to develop. If the Euler product formula were valid, we know it's valid to the right of 1. Suppose if it were valid to the right of the critical line, then by the very same argument that I just gave you for there being no zeros to the right of 1, that would imply Riemann hypothesis. And I'm going to claim that this is true in a certain sense. What I'm going to have to do is, which mathematicians often do, is I'm going to extend the definition of the zeta function. It's really just the simplest example of an infinite class of functions. And in fact, I'm going to consider 2 infinite classes of so-called L functions. And you'll see why. Because in a sense, Riemann, falls into this general class, one of these infinite classes. It's kind of the exception. And the Riemann hypothesis is actually easier for all the other ones, the vast majority. Riemann is a little bit different because of that hole at one. Right? So the two infinite classes I'm going to look at are, well, zeta itself falls into so-called Dirichlet functions. These are all implemented in Mathematica. So chi of n here, n is any integer, is Dirichlet character, defined to be Dirichlet character. It's called a character because it's mapped from a group into the complex numbers. So there's various defining properties. Go back to Dirichlet. It's multiplicative. So chi, the product of two integers, factorizes into complex chi's. Then they're periodic. So chi n plus k chi of n. So k here is called the modulus. So once you fix the modulus k, then the number of distinct characters is equal to the order of totient function. If k is prime, that totient function is just the prime minus 1. So I'm going to give you an example. This is, we played a lot with this example because at k equals 7, there's 6 different characters, and there's enough variation in the characters that you can throw various things. So just, this is, I haven't given you all the properties yet, so let me think it's better just to give an example if you've never seen this before. So here's n this way. 1, 2, 4, 5, 6, 7. We stop there because then it starts to repeat. And here's chi. This one's always defined to be 1. 2 pi over 3. So they're always groups of unity. Okay. Pi over 3. Minus 2 pi over 3. Minus 1 pi over 3. Minus 1, 0. Okay. That's an example. Okay, so they're all roots of unity. They're always roots of unity. So pi of n is always 1. Now, out of these coefficients, these characters, you can define an L function. So you now define a function in the complex plane, just like you did with theta. So it's sine to infinity, but now you just weight it by the character. So zeta corresponds to trivial character as k equals 1. There's only one. Right? This is an example of a principal, and this is going to be important. This is a principal character. So at every integer, every modulus k, there's one principal character, where the characters are all 1, unless if n is coprime to k, otherwise it's 0. Okay, so in that case, there's just 1s and 0s. If you look at this example, this is not a principal character. So at every k, there's one principal character. For high k, there's a large number of other ones which are non-principal. And it's going to be very important to make that distinction. Okay, so so for the non-principal, notice that if you look at these angles, look at these phases, the sum of our chi's up to k minus 1 is 0. Sum of the phases is 0. zero. So it means that these angles here are uniformly spaced on the unit circle. Okay. So if you look at these kinds, for example, in this example I gave, in this particular example, you have -1, you have 1, and then you have, there's 6 different angles represented there, and they're equally spaced. There's a completely different, and there's nothing like this in the principal case because the chi's are all 1 or 0. And this ends up showing up in the fact that the principal case, they always do have a pole at s equals 1, whereas the non-principal guys do not have a pole. So the fact that they do not have a pole opens up the possibility that the domain of convergence of some of these series is actually can be extended into the complex, into the critical strip. I mean, for example, if you consider just L S chi, so how am I doing? Looking at N NDS. These chi's are phases. Look, I mean, if chi is 1, this only converges to the right of 1. But if, for instance, you put in alternating signs, that changes the convergence properties completely. Then the alternating sign test would tell you it converges for real part of S actually bigger than 0. So with these particular characters around, since you have all these phases, it opens up the option that maybe it converges for the real part of S somewhere above 0 inside the critical strip, and then argue that it's actually 1/2. Sorry. Okay, so the other.
Sorry?
Yeah.
The other Euler formula generalizes to this.
Yes, I'm going to write it what it is in a moment. It's important. The other infinite class, which are, I mean, it's nice, you know, somebody might come up with some special proof, you know, for just only works for zeta, you know, but that we somehow fail for all these other classes. So I'm going to give you 2 infinite classes where the arguments I'm going to give work uniformly for all this infinite class of functions. So these are so-called cusp, based on cusp forms. And I'm basically just going to give you an example, but this extends to other weights. Put one here, one example of these for people here. But, so what are cusp forms? So if you look at SL2Z, right, it's so the group of 2x2 matrices with integer entries. So if you have a complex variable Z, not this Z, Z, take C to A, Z, B, C, okay, normally in conformal field theory, we call this tau, but we reserve tau for something else. So a modular form is some function of Z that under this SL2Z transformation, it transforms this way. K, f of C. K here is also an integer. It doesn't have to be though. But K here is now called the weight. And I'll illustrate with one example.
Andrea, probably have Z required matrix.
Yeah, okay, wait, yeah. So this is, yeah, I mean, you mean, yeah. Yeah, right. Yeah, sorry. So one example is based on, well, it appears in string theory, particularly string theory. So let me define Q, as usual, as 2 pi I Z. One of these modular transformations is just a shift in Z, so it means that there's a Fourier decomposition of any modular form. But let me look at this particular one.
Transformation of modular form is not that.
What?
Then when you apply the modulus transformation of f, you get back f, but with the prefactor k. So the first formula was correct.
Yeah, I think so.
Without majors?
No, see,
And when
you take
transform the
Z,
function
this is,
z
if by this, I mean, I transformed Z already, yeah. By this arrow, I mean, I act on Z
yeah,
this way,
you
and
transform
then
the function
you
by
get it
modulus
back up
transformation,
to a
you get back
factor.
f, that's the way.
Yeah, okay, good. Anyway, product of n equals 1 to infinity, 1 to the n, all raised to the 24th power. The 24 is the strings, bosonic strings. Well, you recognize this partition function of the bosonic string, the inverse partition function. 24 is the bosonic strings in 26 dimensions. So this should be somewhat familiar. In any case, you can expand this out. And the coefficients tau n are called the Ramanujan tau function. Okay. So these taus are large numbers. So the taus, you know, the 1, yeah, okay. The math matters so much. To see this, but you know, just so this is, anybody can do this kind of expansion. 252, get a bunch of numbers. They're all integers, but the sign varies. It doesn't strictly alternate. Sometimes they're negative, sometimes they're positive. So we use this partition function to generate these coefficients. And they also have multiplicative properties, but not completely multiplicative, but still enough to have a normal product formula. So you could, for instance, tau n, and tau n. Now only if they're co-prime. Otherwise, this formula is a little bit, has in one other term, which changes the form of the order product, but it's not going to mess up my arguments. So anyway, you define an L function now, the same way. All right. Here, L of S is related, well, what it's just in this case, for this particular tau, this is the weight is 12. Okay, so this is related. There is a functional equation here too. L is not going to write this formula, but it's K minus S. Okay, and K is 12 here. So the critical line, the critical strip is from 0 to 12. And the critical line is sigma, the real part of S is 6. And you can find zeros along this line. And there's a Riemann hypothesis for this too. People believe that it should be true, but it hasn't been checked numerically so much. Okay, so that's meant to be a review. I started a little bit late, but so now I'm just going to just start with the work we did.
And this is easy to prove or not?
What?
What is the conclusion of all this discussion? That for this function, the critical line is difference, no 1/2, but it's always self-dual, this function?
Yeah, no, people know, this is all known so far.
No, but then it's known that all the zero line on the critical
No,
line?
if you could prove it, basically
okay.
you're proving Riemann hypothesis for that function.
Okay, so in a way you're saying there is the same kind of phenomenology also for understanding.
Yeah,
that.
right.
But
So-
the problem remains. It's not.
Yeah, so what I'm going to discuss now is really where our work started so far. But I'm going to show you how it applies to both these infinite classes of functions. So it's not like we managed to find something that works only in one special case, then you're stuck. Okay, so really this is start to get to work. So, well, we're able to prove a theorem. explain this in a moment, but consider this following series. So for Ramanujan, let me consider the series Bn to be the sum 1 to infinity of the sine of this Ramanujan coefficient, Ramanujan tau function, but at a prime. This is important. Okay. For Dirichlet, let me define something very similar. So, I'm sorry. So we're summing up to the nth prime, but now instead of these signs, what's relevant is this character's chi. So remember, chi are always used as unity, so I can write it as e to the I at some angle. So let me consider a sum of the cosine of theta of these angles at the nth prime. Okay. So look at this series. Let's look at the first case. The primes are pretty random. Okay. I mean, if you know that 17 is a prime, that's not enough to predict that 19 is a prime. Given one prime, there's no way to predict what's the next prime. So you're looking at a sum here where this is always just adding a sum of ones and minus ones. But since the primes are unpredictable, even though this is a deterministic series, but because the primes essentially the multiplicatively independent, so that the next term, when you increase n by 1, you can't easily predict what the next term is going to be. And we're going to be interested in letting n go to infinity. Okay. So something very similar here. These are just these angles. Like for this example, there's only 6 possible angles, and you're summing cosines of those angles. But again, you can't really predict exactly what this angle is going to be for the nth prime. So because this kind of this is a way of characterizing what I mean by the pseudo-randomness of the primes. Now in this case, it's obvious if you sum a bunch of ones and minus ones randomly chosen at each step, that's what we call a random walk. And random walks have a typical behavior that, here's the theorem. So if these bn's go to the square root of n, that implies Riemann hypothesis. So I think that's our, and okay, this is important, this is non-principal. No, I think this is an advance because at least we related the validity of the Riemann hypothesis to something it's pretty hard to imagine how it could fail.
What is the theorem? What is the theorem?
This is the theory. If Bn is over the square root of n, this is a random walk property. That implies the Riemann hypothesis is true.
Sorry, you are speaking of the original Riemann hypothesis of the one.
The ones for these, but whenever I say Riemann hypothesis, I mean for a particular class of functions. So for this, all the non-principal Dirichlet cases and all the cases on modular forms.
So the standard one, these tau are all one.
Yeah, so that's why non-principal.
Okay.
I'm gonna have to
That's
return.
applied over.
I'm gonna have to return to Riemann. The original Riemann is zeta itself, which is not contained here. It's an exception. But there's a version of the argument that helps. Okay. But it makes it more that part more tricky.
Andre, this is on the same footing if you would have worked on the Medus function. Exactly the same.
No, it's not.
No, exactly the same, because if you take the inverse of Riemann is the Medus function.
Yeah, but it's proven that the Moebius function actually does not go as square root of n.
Because square root of n plus, I mean, all the devil is in the epsilon that is there. It's exactly the same footing, I would say.
I don't think so. I don't think so. Because the Moebius they're correlated, they're more correlated than these objects.
The argument is the same.
Look, I'm gonna run out of time.
Yeah, sure.
Okay. The argument is not the same. I found this argument anywhere in the literature, but anyway, the proof is, I have to sketch it very quickly. So you consider the series Sn, which is just the real part. Well, you have to start with the other part of the formula. So I'll show you the argument for the L function based on the Dirichlet. So there is no other product formula. Yes. Inverse. Take the log. So then this is going to be the leading term. Log of L. The leading term is going to be the sum of pi pn ps plus something of order 1. Then I'm going to look at the real part. I'm going to consider this series Sn. I'm going to rewrite it as the sum of an bn, where an 1 over pn to the sigma, it's real, and the bn's are cosine of this theta. Now, what I want to do is I want to get these things that I believe behave like random walks. So there's something that came to our help, something called a Bell transform or summation by parts. To a Bell transform, then you can write this as n. You can rearrange the series. So it's the sum of bn an minus an plus 1. So now these bn's now are precisely what I wrote before. It's the sum of these cosines, evaluated. Well, this is at integers. Okay. Now, well, this will wait. Yeah. So bn. So Sn, I'm looking at, this is a sum over primes. Right, so Bn is what I wrote before. It's cosine of the angle at Pn. Now, if you look at the absolute value of this, you can show this less than sigma, absolute value of Bn. And then because this, you have this difference involves 1 over the primes. If you look at the difference, that's going to bring in the gap over Pn sigma plus 1. Yeah, sigma plus 1.
What is the gap?
Gn are the gaps. Now I want to argue, see where this converges. Now there's a lot of interest in the gaps between primes. There's an important conjecture called Kramer-Granville conjecture that says that Gn is less than some constant, well, I'll take to be 1, log squared of Pn. And this has been checked to very, very high end. But it's a conjecture. Fortunately, there's always a sum here. Sorry, this is sum. Up to n. Fortunately, you can do another summation by parts or another Bell transform. And it's sufficient, actually, that a summed version of this is true. And in a separate paper, I prove this. So now, as far as, so this is just get logs. Okay, so Sn goes as sum, but now use Bn is order square root of n. So as far as looking at convergence, you have a square root of n, and then you use the prime number theorem that Pn is order n log n. This comes from the prime number theorem. So you put all this together, you have n sigma minus 1 up to logs, which don't change any of the convergence properties. So because of this extra square root of n coming from the random walk, this converges for real part bigger than half. So you've gone inside the critical strip now. Then use the same argument as before. If the Euler product formula is valid inside the critical strip to the right of the critical line, then the Riemann hypothesis is true. Now, as far as mathematics, pure mathematicians, this random walk property, you're going to have to state it as a conjecture, even though it seems like almost impossible to understand why it would not be true. I mean, it looks exactly like a random walk, but there's no proof of that property. But these arguments tell you that basic Euler product form is valid. You can check this numerically.
Andrea, I didn't get what is better with respect to Möbius.
What?
What is better with respect to the Möbius argument? With Möbius, you have coefficients which are exactly 1 and minus 1, randomly chosen. The problem is that there are random in the gross, the prime number are random. However, there are correlations.
There are correlations,
And
much
this
more
is-
than here. Much more than here for this Möbius. Look, I'm already out of time. We have to discuss this separately. Okay? Certainly, the argument in literature I've seen this argument is not this argument at all. You don't go through this. It's not about convergence of the Euler product.
Sure, but you always rely that they have to be random. So if they are, you do it in whatever manner. But if not, you have always 1/2 plus epsilon. In famous epsilon is there. No matter which function you put it.
In any case, it wasn't by this. This is not the way those arguments go. There's nothing involved by bell transform and all this stuff.
So there could be this epsilon in your case also, and maybe we not modify the tool. I agree with Giuseppe, there is an epsilon, 1/2 plus epsilon.
Yeah, what I mean is, maybe this function is better than Möbius function itself. Okay, maybe. But at the end of the day, you are always using the argument that the prime are random and y should be different. You are using exactly this.
Yeah, that's what I said.
I mean, but if you use it, as I said, also Möbius is absolutely straight. If you use the
No,
random
actually,
hypothesis of prime,
Look,
is
here's another way
always
of saying it. All you're looking at is the inverse of the zeta function.
Yeah.
You're rewriting in terms of Möbius.
yes.
This cannot converge inside the critical line, to the right of the critical line.
We'll have
It
poles.
can't, because it's
We'll have-
poles.
No, I need.
So the fact that it doesn't converge means this argument has to fail.
No, okay, we'll discuss later, but the Boyle line, I think, is always related on the randomness of the prime.
I think so. Now to see how this argument works,
Andre, just to tell you, the
Yeah,
time
I know.
expired now, but we started 5-10 minutes late, so you have
so
to
for maybe
between 5 and 10.
how much, 5 or 10 minutes maybe?
Yeah, just the sign.
Okay. For the modular case, here's kind of interesting. If you try to extend the same reasoning, the same argument works, basically. It goes the same way. But you need one other ingredient that's rather not true here. And it was only proven so I'm looking at the k equals 12, the Riemann case. Here you need that you have to put a bound on tau, because my bn's only involve the sign of this tau. Okay, the growth, or the things converging on, is also involves absolute value. Remember, those are large integers. And you need to, if you use this 11/2, well, it's actually, if you use this result, which was only proven by Levin in 1974, he proved the so-called Weil conjectures, and this was a consequence. So if you use this, exactly the same reasoning applies. Okay. So that wouldn't, again, the Euler product formula is valid. The real part of that's bigger than, well, 6 this time. And because the Riemann hypothesis is valid for those, that class of L functions also. Okay. So I'm not going to have time to talk about zeta. Oh, I should say a little more about it. So maybe at this point, since we'll have a few more minutes, maybe I will actually. Try to quickly go through the rest of the stuff. I haven't given a talk on the board in a while, and I underestimated the time. So I'm gonna have to skip discussing zeta case itself, although we have some results there. Okay. So in an earlier paper, the one that was published in Communications in Number Theory and Physics, we derived this exact equation here, equation 40, for every individual zero. So you look at zeta, I'm talking about zeta now. You take zeta of rho equals 0. So you take the zeros to be, so you look at the zeros on the critical line. So the nth zero is 1/2 plus I Tn. Then we put these zeros in one-to-one correspondence with the zeros of the cosine function and obtained this equation 40. So you choose your favorite zero, you want the nth zero, plug in n in there. This theta is the Riemann-Siegel theta function. It's just the argument of gamma up to a linear term. And you could just solve this equation numerically, and we're able to solve it to very high accuracy for very, very large zeros. It went up to a billionth zero. Now, if what I told you is correct,
Does the formula assume the Riemann hypothesis? I mean, you're only
this does
looking at
not.
zeros.
The way we derived it does not assume the Riemann hypothesis. Okay, I think I have 5 more minutes. Okay, so in fact, this gives you another way to attack the Riemann hypothesis, is that if there's a unique solution to equation 40 for every n, then the Riemann hypothesis is true again. Okay? And that's because you can then count the zeros along the critical line, and the number up to a certain height agrees with a known formula to the backline for all the zeros inside the strip. So I'm going to have to skip that discussion. But it's closely tied to what I talked about before, because notice the Riemann-Siegel term is a smooth function. It's completely under control. Just use Stirling's formula for large t. But you have this arg of zeta term. And notice I'm approaching the critical line from the right. Maybe this is the epsilon you're talking about. It's very important to approach it from the right. The limit delta goes to 0 plus. But now, if the Euler product formula is valid, well, in fact, there's an approximate solution. So if you ignore the arg term, there's a solution in terms of the Lambert W function. Okay, so what? But if I use the order product formula, then I could rewrite this arg term. So here's the same equation I had before, the equation 49. I want to calculate 0 to very high height. Okay, so I use the Stirling approximation for gamma. That's very accurate. That gives the first two terms, the t log t. Okay? Then zeta is given in terms of an infinite product over primes. So I can take an arg and just get the imaginary part of log of zeta. Right? So using the order product, then the arg becomes this imaginary part of the sum over logs of 1 over the primes. I wasn't have time to discuss the zeta case, so there's some, you have to be careful here, you actually have to put it cut off in a very special way. But nevertheless, here's an equation for the nth zero. Okay, we'll finish doing it. Here's an equation for the nth zero that makes no reference to the zeta function itself. Okay? So every single zero knows about all the primes. And I can just try and say, well, I'm going to fix myself. Well, I want to do something not rocket numerical science. You know, I like your terminology there. Just want to do things mathematically that take less than half an hour. So you can use a root finder, fix yourself to a number of primes. And what was reasonable is to take, let's say, the first million primes. Mathematically knows how to do that. Mathematica cannot calculate very, very high zeros, because it cannot implement zeta function itself that high. Okay. But this equation makes no reference to zeta anymore.
Sorry, but in this equation, aren't you using the order product formula?
Yeah, because remember the equation involved arg zeta.
Yes.
So arg zeta is equal to the order product, has order product formula, and I took the log.
But that converges only after real part greater than 1, right?
No, 1/2, that's what I proved. Here I proved that it converges for sigma bigger than 1, a half. If it converged for sigma bigger than 1, there's no point. I wouldn't be talking about it. In any case, you can calculate zeros from this equation. Okay. And compare with some, well, previously I thought the highest record was the 10 to the 22nd zero, which is here, by Lisco. But one of his former students wrote to me and gave me tables for the zeros around the 10 to the 33rd. And the results were very good. I'm kind of limited because I only included 1 million primes. Actually, I'm not collaborating with this student at Lisco to try to do something more tense numerically. But anyway, this gave me enough confidence to go ahead and calculate the Google zero. And there it is. And I'm confident about the last 0.244 because you calculate it using 1 million primes, then you go ahead and use 2 million primes, 3 million primes, 4 million primes. I went up to 5 million primes. And then those last 3 digits don't change beyond those points.
How do you know this is a 10 to the 100?
Because I derived an equation for it.
Yeah, but you don't know that.
I tested against at 10 to the 33rd.
Yeah, but this assumes that you have one solution for your equation for any n between 1 and 10 to the
Well, now that I've
minus 1.
the only way you could
So
not
you assume the Riemann
the only-
Hypothesis up to
the only way you could that would have failed to have a solution is if this arg zeta term was ill-defined. But using this Euler product formula, it's perfectly well defined. I wrote it as an infinite sum of logs, and that converges.
Yeah.
So there's a lot I'm not saying here, okay?
You cannot escape.
There's a lot I'm leaving out, obviously, but it's all in the papers, actually. So anyway, there's the Google zero, for what it's worth. Anyway, it's way beyond the current record, and I'm confident it's correct. So these formulas are working. Okay, thank you.
Thank you, Andre. We are a bit relatively a bit late.
Yeah.
If there is some very urgent question.
Yeah, otherwise I'll be here for
Yeah,
the
exactly.
next few days. We can talk in private.
Questions? No? But do you ever read emails?
What?
Do you ever read emails?
Yeah.
There are 20,000 unread emails.
What email? What?
You have 20,000 unread email in your inbox.
Oh.
Never saw
I
this
don't
number.
read any from you.
Is it just the number you employ the employee?
Ah, okay.